So today I want to talk about machine learning in uses in experimental analysis. And as is tradition among economists, I'm going to motivate my talk by an empirical fact. Empirical fact I'm going to motivate it with is just the amazing availability of very high quality prediction tools, particular machine learning, artificial intelligence tools. So this is a family in Japan who harvest cucumbers. So I got that story from last week's New Yorker. And in Japan, apparently, it's very important to appraise a cucumber by its visual quality because that's very determinant of its price. So usually the mother in that picture on the right is a person who goes to the field and appraises all those cucumbers. Now, her son on the left automated that procedure by building a tool that automatically takes pictures of these cucumbers and then feeds them into a neural network and classifies them by their quality. So, of course, this thing uses TensorFlow. And apparently, it's so easy to do that these days that my favorite YouTuber here claims that coming up with such an image recognition software takes mere 5 minutes. So that is the first empirical motivation for my talk, simply that state-of-the-art machine learning tools are now readily available. Now, from an econometrician's perspective, it is remarkable that the innovations behind these advances in artificial intelligence are actually more statistical in nature than anything about what I had before associated with computer science. So in particular, these advances are driven by inducing rules from sample data rather than inducing them from theory. So in the end, these tools look very much like the statistics that I'm using in my econometric work. And that raises a question how I can leverage those innovations in working with very high-dimensional data in the statistical problems that I typically come across, in my work. Now, when I think about how to use machine learning tools in my work, there's a big divide, which is that supervised machine learning, at least, focuses mainly on prediction. So I want to find some rule that connects some characteristics of data points to some outcome that I want to impute, such that the imputed outcome is very close to the actual outcome. For example, I may want to take a picture of a cucumber and then appraise its quality. I'm doing that by first training that on a data that is, in this case, generated by the mother in that picture, who appraised many cucumbers, and I take pictures of it, and I learn a rule that relates that picture to that quality. Typically in economics, we focus much more on parameter estimation. So we're interested in some structural parameter that underlies the relationship between covariates and outcomes, and we want to make inference on those in order to answer causal questions. So for example, rather than checking, like, given that cucumber, what is its quality, I may want to answer a question like, should I use more fertilizer next year in order to increase my yield? So question here really is, how can I use such prediction tools from machine learning in an estimation problem where I want to have an estimator of some structural parameter that has some robustness property? For example, I may want it to be unbiased, or at least I want to have some guarantee that as my sample size increases, eventually I'm going to find the truth. There have been different attempts of integrating machine learning into economics that I broadly classify into two categories. The first category is simply directly using prediction tools when the question at hand is actually reasonably thought of as a prediction question. For example, rather than asking, should I use more fertilizer or not, I may actually try to answer the policy question, which of my many, many fields should I use fertilizer on and which one not, which would be a relatively direct prediction question. So that is generally conceptualized as prediction policy problems, where a prediction function itself is the policy that I want to run. There are also very innovative uses of prediction tools to test theories. So Annie earlier today presented one idea. Alex also has a paper on that. There are also attempts to more indirectly leverage predictability as an interesting quantity in economics. For example, I have a paper on formalizing multiple outcome tests as prediction. And more fundamentally, we also have seen talks yesterday of just using machine learning as a data preprocessing tool where I turn interesting data like pictures from Street View into usable data in the first place that I can then feed into my economic analysis. What I'm going to focus today on is a second category, which are estimation tasks where I'm interested in some parameter like an average treatment effect, what is the value of adding fertilizer to that field, but there is an implicit prediction task behind it. That has also been done over the last couple of years. For example, Susan Athey and Guido Imbens have a paper on analyzing treatment effect heterogeneity using ideas from machine learning. Viktor Chernozukov and co-authors have work that is very related to what I'm going to present today on taking care of high-dimensional controls in data where you think that treatment may actually not be assigned randomly, but you want to correct for the fact that there are section effects. And finally, there are instrumental variable strategies that are very popular in applied economics, and that basically have an underlying prediction problem where you project some endogenous regressor on some exogenous instrument in the first stage. If I have enough time, I will get to that in the very end. So in my talk today, I want to make a very precise duality between one estimation task and one prediction solution for the specific case where you want to take care of high-dimensional controls that you have collected about your subjects in an experiment. And that work that I'm going to present today, the technical parts are closely related to classical results on shrinkage in statistics and to more recent work on model averaging in econometrics. And while the results I'm going to present will be fairly narrow in their assumptions, I think that some of the takeaways on the agenda here is more general and can lead the way in terms of integrating some of these machine learning prediction tools into applied economics. So the workhouse of applied econometrics is linear regression. We have some outcome y and some right-hand side variable x, and we are interested in estimating some structural parameter that connects those two. In this case, I call this beta. And we know that if we restrict ourselves to certain well-behaved estimator like linear estimators, and we want to have an unbiased estimator for beta, then OLS is usually the best by the Gauss-Markov theorem. Indeed, it is the one with the lowest variance if we restrict ourselves to unbiased estimators. We also know that if we drop that assumption of unbiasedness and instead, for example, we focus on only predicting, so rather than wanting to get good inference on this parameter beta, all we want is for a new instance where we know x, we want to impute y, and we want to do so by minimizing the distance between y and y hat, that then OLS is actually inefficient and there are better estimators at that task, even if the data is exactly as it is written here. And the two main results here is, first, for the efficiency in estimation, the Gauss-Markov theorem which says that any other linear unbiased estimator of beta has a higher variance. On the other hand, if I care about prediction, meaning I only want to minimize forecast loss, then provided that the parameter is high dimensional, which in that classical literature has dimensionality at least 3, and that noise is normal, then there is an estimator that effectively shrinks. So it solves a Bayes variance trade-off close to optimally and thereby strictly improves. Now this is very far away from TensorFlow and some very non-parametric applications, but some of the insights that I hope to provide you with today I think generalize to that more general setting. So let me just give some machine learning interpretation to what I just said. So in machine learning, we would call shrinkage regularization. So we want to control the complexity of the functions we use so that we don't overfit. And we would use the data to choose the complexity, which in machine learning would be called tuning, and here is simply achieved by some formula that connects the data that are observed to the shrinkage factor. However, in most of the applications I care about, the world actually doesn't look like that there's a single high-dimensional parameter and I either want to estimate it or I want to predict. In most cases that I care about, there is some low-dimensional parameter I care about. For example, an average treatment effect. What is the effect of using fertilizer on that field? But then there may be a very high-dimensional vector of controls that I can use in order to reduce the variance of my estimator. So that may be information about people in my experiment. So even if I randomize who gets treatment and who gets control, I may still have that high-dimensional vector of controls that I want to use. So in my talk today, I'm going to start with that linear framework. I'm going to turn this estimation task on beta, where I really only care about that low-dimensional parameter beta, into a prediction task in gamma. I will, by the way, show that OLS here is unadmissible even among unbiased estimators, provided that I have assigned treatment randomly. And I'm going to interpret the resulting estimator in two different ways, connecting it to the existing literature, as a model averaging estimator as well as an empirical Bayes estimator. And finally, if I have enough time, I will also discuss extensions to non-parametric predictors, where you can actually take this not as literal as I do now, but think about using any prediction technology in order to solve your prediction task, and also contrast this with shrinkage in instrumental variable estimation. So the main theoretical corollary that will come out of the analysis today will be that if I assume that treatment is assigned randomly and I have a high dimensional vector of controls, high dimensional here meaning at least 3-dimensional, and I only care about estimating my parameter beta, then I can find an estimator that has lower variance than OLS. And I can do so by shrinking in the gamma parameter, but I can do so in a way, and that's what I want to focus on today, that doesn't induce any bias in beta. So that implies that linearly squares is dominated in terms of variance if you just have a one-dimensional target parameter that you care about. And that is in cases where you have some kind of identification, where you have some kind of randomization, so that you can reasonably assume that treatment is assigned as good as randomly. I should also highlight that the assumption here that treatment is assigned randomly is necessary. If I really rely on the unbiasedness property, then I will not be able to get a better unbiased estimator in cases where there is generic correlation between treatment and control. So that is one corollary that may be of some theoretical interest, but what I want to focus on more today is actually to show that this result is tightly connected to a prediction task in the background, and the reason why we are doing better at estimation here is that we have tools that do better at prediction than OLS. If you are well known to the more classical statistical literature in that field, that result has a slightly different flavor from this classical result. So even if you don't care about unbiasedness at all, you just care about getting a good estimate of your low-dimensional parameter beta, we know that OLS is admissible, so it's not dominated by any other estimator, provided that the target parameter is very low-dimensional. So in particular, if the target parameter is 1 or 2-dimensional, then you cannot generally do better than OLS, even if you have a very, very high-dimensional nuisance parameter. That is in stark contrast to the result here, where even if you have just one parameter, it's really the dimensionality of the nuisance parameter, so the dimensionality of the controls, that matters for the question whether you can do better than OLS. So let me now line out what I mean by bringing prediction into estimation. So I'm making some assumption on the data. Here I'm assuming that I have a linear model that generated the data. And I want to discuss some estimators for which I make some robustness property. In this case, I want to have estimators that are unbiased, so on average they get it right. I also have some loss function in mind. So for the specific case where the dimensionality is 1, I just want to get as close to the truth as possible on average. Since I've already fixed unbiasedness, that would just mean minimizing the variance. So among unbiased estimator, I want to find one that has low variance. And then I have some technology available to myself that I conceptualize as purely minimizing out-of-sample prediction loss. So from an economic perspective, I can basically think of this as a utility maximizing agent. So I have access to somebody who I don't really know what that person does. All I know is that person provides me with great predictions on a new sample point from the same distribution. And this is going to be my conceptualization, what machine learning does for me in that talk today. And so the question is going to be, how can I leverage a good predictor, f hat, when my goal is actually getting a good beta hat? And there's one first approach that I could take. I could take my equation with a y on the left, treatment on the right, some controls on the right, and I could simply use my machine learning estimator, throw everything in, come up with a good model, f hat, that predicts y from treatment D and controls X, and then look at its coefficient and looks how it looks like. So as long as I'm doing something that provides me with linear coefficients, that may be something I'm tempted to do. The problem here is that if I'm using methods that in a data-driven way, for example, use shrinkage or selection, like the lasso, then this can create bias or omissions. For example, it could be that the estimator on treatment is not included in my model at all because that model at the given sample size found it more valuable to include more controls rather than my treatment indicator. So in that case, the prediction and the estimation tasks are not well aligned. The out-of-sample prediction quality of the function is not the same as getting beta hat close to beta. So there's a more general point here that I want to make by extension about machine learning, although I've only shown you this very narrow example, which is that exactly the features that make machine learning work and predict very well on very varied data, using very flexible functional forms like neural nets, using regularization, which controls the complexity, and doing so adaptively, so tuning from the data, are exactly features of machine learning that make it very, very well suited to high-dimensional prediction tasks that we cannot do with our classical linear regression type tools. But they also make them a challenge to use when we want to get interpretable coefficients out of them. So typically, these may be unstable because they're sometimes just not chosen and not used at all, may be inconsistent, not converging to the right truth, or even if I have coefficients that look reasonable, they may be very hard to interpret because I would have to use like knowledge about correlations to give them good interpretation. So there are certainly ways of fixing that and of asking how can we use some of these insights in order to come up with tools that give us good insights about coefficients. For the talk today, I'm really going to assume that all I can assume for my machine learning stage is that I obtain a good prediction. So therefore, I'm going to advocate a second approach, which is I try to transform the problem that I have into a prediction problem such that there's a one-to-one correspondence between estimation of my parameter beta and prediction in the component that includes the gamma. So let me just propose this very simple class of two-step estimators. I could, for example, first estimate my component gamma by some gamma hat, and then I simply take out x prime gamma from my y, basically taking care of the component x prime gamma that I think right now only adds noise to my regression, but is not something I care about intrinsically. And then I regress these residuals on my treatment in order to obtain an estimator of beta. So what I'm going to claim, I'm going to show you that if I set that up in the right way, I set up the loss function in the right way, then there is a prediction problem behind that is exactly one-to-one aligned with my estimation task, provided that treatment is orthogonal to the controls. So I'm now, to be able to do that, give you basically three slides of matrix algebra. If that is something you enjoy, then that's great. If not, then I think I will be able to get you back in 3 slides. So here I'm just going to write the same data joining process in this matrix form. I've also assumed here that the controls conditional on treatment are normally distributed, and also that these two are orthogonal to each other, so they don't have any correlation. And I now start out with 3 basic estimators that are like natural estimators you may want to run in that case. The most natural estimator would just be to run a regression of y on d and x, and then look at the coefficient on beta in order to get an estimate for that parameter. You could also say, well, in this case, why do I use the controls at all? You told me that you have independent treatment, so I can simply take basically the difference between treated and control, which would just be running a regression of the outcome y on my treatment d and forgetting about x altogether. I call these two like the long regression and the short regression. Then there's a third regression, which is probably the best we can hope to do, which is the one where I already know gamma. So basically, I give you that data, but I also tell you what gamma is. So the best you could probably do is simply taking out x prime gamma from your regression. So the two-step estimators that I just showed that consist of first predicting y using the x, taking residuals y minus y hat, and then regressing that on d, exactly correspond to 3 different, so in that framework, the 3 estimators I just mentioned exactly correspond to 3 solutions of that first stage. So for O less, I would solve some residualized regression of y on x. For the short regression, I would simply take an estimator of 0 in the first stage. I simply don't run it at all. And for the oracle regression, I would simply take gamma itself as that first stage. So far, basically everything falls into that framework. But I haven't told you yet what the right prediction problem is and how can you use that to improve. So let's look at what we want to obtain. We want to obtain a low loss in my beta hat that here I'm evaluating according to a norm that is natural. So basically, I'm weighting the different components by the empirical covariance of the treatment. If that was just one-dimensional treatment, then this would simply be the variance. So what we want to obtain here would be low variance. And this is a generalization to multiple dimensions. So it turns out that the loss in estimating beta by beta hat that I've created in that two-stage form is exactly the loss of predicting x gamma plus epsilon, so x gamma plus the noise by some x gamma hat, but projected onto the space that is spanned by treatment. So let's look at what I would obtain here if I use the OLS solution for the long regression. By the Fisher-Low theorem, I could write that as exactly solving a prediction problem where I also predict x gamma plus noise by some x gamma hat, but now not projected on D, but exactly in the orthogonal space that is residualized with respect to D. And the OLS solution here would consist of simply taking the in-sample loss minimizer and plugging it in. So I'm now taking that insight and simply writing this as a general prediction problem using some orthogonal matrix that exactly creates a diagonal matrix from the projection matrix onto D. I basically divide the data into the data projected onto treatment and the data orthogonal to treatment. And now the loss I really care about, which is the loss in predicting beta, turns out to be a prediction loss summed over dimensionality of B many points in predicting x gamma plus epsilon from x prime gamma hat. But I obtain an additional n minus dimensionality of beta many points that I can train that model on. So because I assume that treatment and controls are independent, exactly because of that property, I actually know that those two data sets are exactly IID and in particular distributed in the same way. So now if you didn't follow the algebra and the rotation here, let me try to get you back here. So what I have shown you is that I can somehow transform the data in a way that is feasible, so I know everything about the data that I need to know to do that, such that I obtain a training set of n minus dimensionality of beta many points. So let's just call dimension of beta 1 for now. So I obtain a training set of n minus 1 many points, and then the loss that I obtain, in this case the variance, in estimating my beta will exactly be the prediction loss according to that same distribution on the nth point. So I have a training sample of n minus 1, an additional point number n. The estimator will always be unbiased if I use that residualization strategy. The thing I care about, in this case the variance, will exactly be a scaled version of that out-of-sample prediction loss. And the distribution in the training sample and in that additional data point will be exactly the same. So that just means I have now reduced the problem to an out-of-sample prediction problem. That's not specific to being able to run OLS in the first place. I could have done the same transformation even if the nuisance parameter would be very high dimensional. And also that prediction estimation tasks are now perfectly aligned under that transformation, so I can basically use any high dimensional predictor in that first stage, and I know that as long as that predictor gives me a good out-of-sample loss, it will be exactly the right thing to use in my estimation task. So let me now prove the corollary that I presented you in the beginning. That was that OLS is inadmissible in that case, even among unbiased estimators. So the loss that we aim to minimize is exactly proportional to the out-of-sample prediction loss according to that distribution that I defined. The OLS first stage estimator takes n minus 1 training points and returns the in-sample loss minimizer according to the distribution. So it would be the maximum likelihood estimator in that distribution, and that plugs that in. Now we know that if we care about out-of-sample prediction loss, maximum likelihood is inadmissible because we can do better by some shrinkage. So the intuition here is that using OLS for out-of-sample prediction would overfit. It would basically pick up too much of the error when constructing the predicted values. And we can do strictly better by by shrinkage. Of course, it produces some bias, but by our construction, that bias in the first stage doesn't matter at all. In the end, we only care about beta. In particular, there are shrinkage estimators that simply take the OLS solution from the first stage and shrink them towards 0. And that effectively yields an estimator that averages the long regression with the short regression. So you can think of what I just did in the case where we are low dimensional enough to be able to run these regressions at all, as basically taking the long regression and shrinking it towards some other regression that we know is also unbiased in that case and has, we think of as usually less precise, but there is some point in between those two that actually produces lower variance than any individual of these regressions as, under some assumptions. So in particular, there's the famed James-Stein estimator that provides us with a shrinkage factor that we can use that guarantees that we always get better prediction loss than the long regression. And using that, or a version of that for out-of-sample prediction, I'm able to prove that theorem. So that means that dominance in mean estimation according to squared error loss translates into dominance in unbiased estimation in that case. So for those of you who see machine learning more through an empirical Bayes perspective, I can actually give an empirical Bayes interpretation to that estimator that also provides some other interpretation of unbiasedness if it's some property you usually don't care about. So you can also think of the estimator I proposed here as a generalized Bayes estimator where you put some prior on the beta, the parameter you care about, that is uninformative. So in this case, it would be an improper prior that is Lebesgue measure. So you're basically saying, I'm willing to put prior on my problem only in those dimensions that I don't care about. I put a prior on the nuisance parameter on the control, the gamma, and I do so in a rotation invariant way in order to basically honor the invariance properties of my problem, but I am not willing to put any information in the target parameter. And if I do that and I turn it into an empirical Bayes estimator where I use a very specific sample analog to estimate the covariances, then it turns out that I exactly obtain the James-Stein version of the first stage. So therefore, if my treatment is orthogonal to my controls, I can connect the uninformativeness property that we may find very appealing intuitively to the unbiasedness property that some of us may find appealing and others less so. Of course, I've made a very, very strong assumption. I've assumed that we are in a world where treatment is assigned randomly. For example, a company running a drug trial and assigning who gets treated with a new drug randomly. These transformations are also feasible when treatment is not orthogonal to the controls. But the question is, what goes wrong? Like, why can I not achieve the same results? And the reason is that if I start to consider a case where treatment is not orthogonal to the controls anymore, then in that out-of-sample prediction exercise that I gave you, where I said I train on n-1 points, I predict on a new point, the distributions of this training set will be different from the new data point that I obtain. And I can therefore not solve that directly as one out-of-sample prediction problem where the new distribution is the same as the old distribution. And fixes in that case basically involve solving some auxiliary prediction problems. So the research by Viktor Chernozyukov and co-authors I alluded to in the beginning exactly does that. It basically says, in that case, we should solve two prediction problems simultaneously. There's another drawback to what I just showed you, which is probably the biggest one. I made this very strong normality assumption. So if we have some drug trial, for example, we may want to believe in the assumption that I've randomized that I've randomized treatment. That may also in other cases be given by some natural experiment that we exploit. But we usually don't want to rely in our inference on assumptions that say the data is truly normal. So we could simply augment the two-stage procedure by sample splitting and say, when we come up with a prediction of the ith y unit, we simply don't use any of the data that pertains to the unit itself, but we only use all the other data. And if we use that construction, it turns out that the loss function is something we have to derive and may look slightly different depending on the specific sample splitting we use. But in the end, we can still do the same and obtain an unbiased estimator that avoids bias, where the prediction is perfectly aligned with estimation. So in that case, we may be very comfortable in using any high-dimensional prediction tool that does well at that prediction exercise in order to obtain an estimator that is still unbiased, even if our normality assumption fails. I now want to end on contrasting the results I just showed you with another application of high-dimensional prediction that is very common in economics, in particular econometrics. So in many cases, we may not have randomization of treatment. So just running a regression of my outcome on my treatment has biases that come from selection into treatment. However, if, like in this setting, we have we have an instrumental variable available to us, we may be able to fix that by using that instrumental variable. So what is the problem here? The problem is that I have some treatment that is correlated with the error term here. And that correlation comes from, in this model, from a correlation of the first stage noise term and the second stage noise term, E and F. So they may have some correlation. And therefore, if I simply regress Y on D, I will obtain some selection bias. Now, I also have that instrumental variable Z here. And I've assumed here that Z is uncorrelated to the error terms E and F. So what I could do is I could project my treatment onto these instrumental variables Z and then regress my Y on those projected variables. And the idea here is that this also can be thought of as a first stage prediction problem, where effectively in a first stage I want to predict treatment from the instruments, and then in a second stage I use that in some way to obtain an estimator of beta hat. When I do so by using linear least squares in the first stage, so the equivalent to the long regression before, I obtain the standard two-stage least squares estimator, which is basically what people in applied econometrics use in that case. However, there's now a nonlinear mapping between that prediction and the estimator. So in particular, it's not just that I residualize the outcome in some way and then I regress it on something, but I actually may now regress the outcome on something predicted, so that may appear not only in the numerator, but also in the denominator. So the result I can present here is actually that if the instrument in the first stage is high dimensional, then I can construct an estimator using James-Stein shrinkage that is not necessarily lower variance, but that has lower bias. So I've now shown you one result where I showed, like, for controlling, you can do something with your controls in the first stage, shrink, and you will obtain a lower variance estimator, which seems very natural because we associate shrinkage with reducing the variance. I've now shown you a second result that goes in the other direction that says I can shrink in the first stage, which we associate with variance reduction, but what I get out of it is an estimator that has lower bias. So let me clear that up. In the case of controls, I told you that high variance comes from overfitting. So we think that the predictor we use in our first stage, which here was O less, picks up too much of the noise and should pick up a little bit less of the noise, even if that induces some bias. In IV, if the first stage overfits, which means that my predicted endogenous regressor, my predicted D is too close to the actual realized D, so I'm picking up too much of the noise F, then what happens if we turn that to the extreme is simply that the regression I run from Y on that predicted element is simply going to be the same as O less. So I'm going to recover the original selection bias that I would have had I never used the instrument in the first place. So overfitting for instrumental variables produces bias in that second stage because of the nonlinearity in the mapping between that first and that second stage. In both cases, however, a better prediction in the first stage yields less overfitting, which in one case results in less variance, which is great, and the other case in less bias, which is also great. So let me conclude. I started out with the fact that we now have many high-powered prediction tools very widely available that work great and better than some of the old tools we were using, especially when we have very high-dimensional data. There's a big challenge, however, in using those in the typical tasks that we deal with in economics, which is that we typically care about estimation quality, and these tools provide prediction accuracy. So the question, how can I turn prediction accuracy into estimation quality? And one problem that a naive approach of that, basically simply treating my estimation problem as a prediction task, is likely to lead to biases and misinferences. As one solution, I proposed today to carefully basically transform your estimation problem into prediction tasks. And I did that in that very stylized normal setting, but I think the insights generalized. So for me personally, next steps in that project are now to use some real-world data like RCTs and to see how large are the likely gains from using such methods over using standard regression analysis in the typical applications that we have in mind in economics. So thanks for your attention, and I'm happy to take questions.
Awesome.
Alex?
So one reason that people love these unbiased estimators is you can do inference on them really easily. But it seems like once you start doing the first stage, it becomes a lot harder to get confidence intervals and stuff like that.
So that's a great point. I think in my case, I make it somewhat easier. So let's go back to the prediction lemma. So I agree with you in general, we may be worried because now we need inference not just on the estimation part, but also on that high dimensional prediction component. Exactly, and that may cause trouble. However, if here you're interested in making inference only on your beta head, I've basically shown you the variance of that is exactly an out-of-sample prediction loss. So you can basically use an unbiased estimator of your prediction loss in the first stage to get a valid standard error in that case, because your variance turns out to be exactly prediction loss. So in some cases that may be like a worst case bound, and I haven't claimed that this will be asymptotically normal under the most general assumptions. But if you're just interested basically in estimating a variance, that in this case you can construct some out-of-sample prediction error measure, which we know is available in unbiased form, for example, from sample splitting. So if in my first stage I use cross-validation to come up with an unbiased estimator of my out-of-sample prediction error, I could plug that in here and say this is basically a standard error. Now, that doesn't necessarily mean it's asymptotically normal in everything, and it may be worst case in some cases that are less parametric than this. But I think if we are careful about this mapping, there's a hope that all we need to know is how good is the prediction, because that's all that matters for the estimation.